Okay, so recall we are in the middle of learning our very first new reaction, free radical halogenation. We opened this handout with a reaction you guys should know really well, and those are acid-base reactions, and importantly here we're moving 2 electrons all the time. And free radical halogenation, remember, just in general, is just a substitution of an alkyl H being replaced with a halide, and you do this with the diatomic halide, and then you need some light to get this going. Interestingly, right, we saw one that actually gave 2 different products, interestingly. And so how does this reaction work, right? Remember, it's got 3 basic steps. We've got initiation, propagation, and termination, right? And then there were 2 propagation steps. But initiation, remember, was just the diatomic halide splitting or homolytically cleaving into 2 radicals, right? Each atom got 1 electron, okay? We needed light to do this, and this was the initiation. Again, it got us going, and it made that very reactive intermediate. Okay, we had that important side note of the difference between homolytic and heterolytic cleavage. Again, homolytic, we're moving 1 electron, and heterolytic, we're moving 2 electrons. So we use half arrows for this handout. We're using all half arrows. So that was initiation. And remember, we made chlorine dot. And then our 2 propagation steps, right? We need to continue the chain reaction. So chlorine dot reacted with methane to make methyl radical and a product, HCl. And then the methyl radical reacted with another equivalent of the chlorine, not Cl dot, right? Because we want to keep the chain reaction going. So it reacted with chlorine, because again, there's also more of this in solution, to make our chloromethane, and then a new radical, the chlorine dot. And then we had to show our termination steps. Again, we don't want these really, but if I ask for them, you have to draw them. Okay, we showed how this can be a continuous mechanism, just as long as you label your steps, no big deal. And finally, we talked about other proposed mechanisms and how do we discern between different mechanisms. And it's really the energies involved, okay? So we looked at our 2 propagation steps and we calculated their delta H's, the enthalpy of each step, right? In that first step, the slow step, was only endothermic by kcal per mole. And so I proposed this other possible mechanism where instead of making a methyl radical, we make an H radical. And this was highly endothermic, this step, right? It has a enthalpy of positive 20 kcals per mole. So this is very endothermic, so it's very unlikely. All right, so recall again on that first page how we had that example with 2 different products. So the bottom line is that as soon as we move past methane, right, because methane just has 4 H's on it, but as soon as we move past methane, we have an issue of selectivity. So I'm going to redraw that reaction we just had there. Overall reaction. So that when I have propane with Cl2, throw it in with some light, right? We get 2 products. We get this product in 60%, and we get this product in 40%. And of course, we make some HCl. Okay? So it's this issue of selectivity. So why do we even have more than 1 product? Why? And the truth is, it's because we actually have different hydrogens on propane that can react. There are different hydrogens, okay? Different H's on propane, okay? How are they different? It's the type of carbon to which they're bound, okay? So here's a big old drawing of propane. These hydrogens over here, on what carbon, on what degree of carbon are they? What degree of carbon is this guy right here? He is a primary carbon. And so is this guy. These are primary carbons. How about that carbon right in the middle? What degree is he? He is a secondary carbon. Well then, the hydrogens on those carbons also have the same degree. I don't know why it's moving out of focus. Come on, camera. Refocus. All right. These hydrogens right here are primary hydrogens, okay? Because they're on a primary carbon. This guy over here, and these guys up there, okay? The ones on the left here, again, are primary hydrogens because they're on a primary carbon, and these guys right in the middle are secondary hydrogens because they're on secondary carbon, okay? So these are different, okay? They do have different reactivity because you can see here, the one that gave us the most product, it was a secondary H that was replaced. And then the one that gave us the smaller amount of product, only 40% of the product, it was a primary hydrogen that was replaced. And it could have been from either side, it doesn't matter, it's symmetrical. Okay, but again, we only have 2 secondary hydrogens, but yet they accounted for 60% of the product. And so that's interesting. If we think about their relative reactivity, if we compare, again, how many hydrogens made how much of each product. Okay, so the primary hydrogens that could have been replaced made 40% of the product, and that's it, divided by 6 possible hydrogens that could have been taken. And we get this reactivity of only 6.67% of product was formed per H. Okay, if we use the same argument for the secondary hydrogens, okay, they actually counted for 60% of the product. Whoa, 60% of the product. And there were only 2 of them, 2 secondary H's. So each H then actually accounted for 30% of the product per hydrogen. So if we can then do a direct comparison, if we divide 30 by 6.67, we actually get 4.5. And so this tells us actually that those secondary hydrogens are 4.5 times more reactive than the primary. Okay, because again, they accounted for that much more product. Okay, they formed more of the product. Okay, so the secondary H's are 4.5 times more reactive than primary hydrogens in chlorination. And I am going to be specific because it isn't the same for bromination. So I'm going to be specific for chlorination. Okay, so the burning question is why? Why are the secondary H's more reactive? Okay, and you can see here in this next line, it has to deal with their stability. Okay, because again, if you are a reaction and you're going through your mechanism, you're going to want to take the most stable path. Okay, you want to not expend too much energy, you want to take the most stable path. So there must be difference in the stability of those free radical intermediates. Okay, and it's true, there is stability differences in those free radical intermediates. Okay, because of free radical stability. Okay, because these are the intermediates of our mechanism, so there must be something different going on. Okay, so let's think about those intermediates and what they look like. Okay, if we again consider the different hydrogens in propane, okay, we have our primary hydrogens, okay, and so when they react, okay, primary H's make this type of radical right on the end. This is a primary radical. Primary radical. Okay, if you look at him closely, you want to draw the hydrogens. He's only got 2 on the end there because again, it was that third one that went and formed HCl because it reacted with chlorine dot. Okay. What about those secondary hydrogens? Can you guess what kind of radical they make? Right? Secondary H's make, here you go, right there. Okay, if we look at him a little bit closely, he's only got 1 hydrogen. And yes, this is a secondary radical. Okay, so those are our only 2 options. Okay, those are the only 2 types of hydrogens in propane. Okay, so chlorine dot can either react with those primary hydrogens or it can react with the secondary hydrogens. So why does it prefer to react with the secondary hydrogens? Why does it prefer to make the secondary radical? That's because radicals are electron deficient. Okay, this becomes important. So radicals are electron deficient. Again, they are unpaired electrons. So they definitely want more electrons, okay? So they're stabilized then and are thus, thus stabilized by electron density, okay? By donation of electron density. Okay, so if there's a polar group that can maybe donate some electron density, sure, that would be great. But even an alkyl group, I know we're not talking very polar here, there's just carbon-carbon bonds, but the more carbon-carbon bonds that we have, we can actually donate electron density to that radical. Okay, so here it's right in the middle, we can have these two carbons donating electron density, whereas on the end here we only have one carbon that can donate its electron density. Okay, so it's stabilized by donation of electron density from alkyl groups. Jeez, I have to type and write and speak at the same time. From alkyl groups or resonance. If you can get stabilized by resonance, absolutely, that will win each time. Okay, it definitely contributes to the stability of the radical. So if you can delocalize that radical, that definitely makes it more stable. You can delocalize the radical. Okay, so in terms of stability between the different radicals you can make, okay, the least stable radical you can make is the methyl radical. It doesn't have any other alkyl or anything to donate electron density to help stabilize it. What's the next least stable? It's a primary. Because again, we're only bound to one other carbon that can donate electron density, followed by a secondary radical. Okay, and now the more stable ones are the tertiary radical, tertiary. Okay, and then we can also do benzylic, or sorry, next to an aromatic group, or allyl. That's in your homework. We can go over that. But let's label these again. Again, the methyl radical is the least stable because there's nothing to donate electron density to make it more stable. Again, these are electron deficient, the radicals, so the more alkyl groups or more electron density they can have, the more stable they will be. So this is a primary radical, primary, here's secondary, and tertiary. Okay, so this guy is definitely the most stable. Again, the more alkyl groups you have, the more stable you're going to be. And this can be seen in their BDEs. Okay, so this methyl radical came from methane. Okay, and methane has a BDE of 104 kcals per mole. Whereas the tertiary radical, right, came from, well, this guy. And in general, if these were all methyls around it, this guy has a BDE of 91 kcals per mole. Okay, and then the trend fits in between these two as well. So they are in between 104 and 91 for these guys. Okay, so the methyl radical bond, sorry, the methyl H bond, CH bond of a methyl CH bond of methane is the hardest to break. Hardest to break. That's because if you think about a reaction energy diagram, do you think it wants to go to the least stable product? Right? It doesn't want to go there very often. So it takes more energy because the product is so unstable. So it takes more energy to get there. Whereas the tertiary guy, it's not as unstable. So the energy it takes to get there is not as much. That's why these guys are the easiest to break. Okay, so the radical stability is inherent, as it can already be seen in their BDEs. Okay, again, the more electron density we have to be donated from alkyl groups, the more stable the radical you'll be, and that's because the radicals are electron deficient, and we can see this in their BDEs. If you have a bigger BDE, then you are an unstable product. Okay, so you're not going to be easy to break. Okay. So the stability of that radical intermediate plays a large role in determining which product you're going to make more of, but so does the number of each hydrogen present. Okay, so it's also a numbers game, because I know that we had 6 primary hydrogens over here, you know, but we have 2 secondary hydrogens, but these form the more stable product, so why doesn't it just go through this secondary radical all the time? And that's because it's also just kind of random in the sense of it finds those primary hydrogens also somewhat regularly, right? Because those radicals are really reactive. They just want to find something and go and react with it. So it depends upon the number of hydrogens that can also be present. So what if I gave you this guy, okay, and I told you that primary hydrogens are about 5.5 times more reactive than primary. Okay, right, so these are even more reactive than secondaries. Well, just compared to primaries, because I'm telling you they're 5.5 times more reactive. So they're 5.5 times more reactive than primary hydrogens in chlorination. Okay, can you provide me with the product ratios? Product ratios. Okay. So let's count up the different types of hydrogens and the amount that there are. So this is called isobutane, the starting material. So the H's and their number in isobutane. Right? There's a whole ton of primary hydrogens, right? We have these 3 up here. These are all primary because they're on primary carbons. Here's another set of 3, and all down here. Okay, so there are 9 primary hydrogens, right? 9 primary hydrogens. How many tertiary hydrogens are there? Just 1. This guy right there. Just him. Again, he's on a tertiary carbon, so he's a tertiary hydrogen. So he has 1 tertiary hydrogen. All right, so let's think about how many there are and multiply it by their reactivity. Okay, so we have 9 primary hydrogens. Multiply it by their reactivity, and we just get 1 because it's 5.5 times 1. That's the tertiary hydrogens. So 1 time reactivity, and we get 9.0. But if we do the same argument for the tertiary, so we have 1 tertiary H, multiply it times its reactivity, 5.5 times reactivity, and we get 5.5. Okay, so then to figure out the product ratios in terms of percentages, we need the part over the whole. Okay, so combined, these guys have 14.5 possible kind of things. We just need the whole, right? So then, if we do 9.0 divided by 14.5, because it's the part over the whole, we get 62% of this guy, just coming off of any one of those primary carbons, just coming off of any one of those primary carbons. And for 5.5, we get 5.5 divided by 14.5. And we only get here 38%. Okay, so 38% of your product will be this guy. Okay, so even though the tertiary hydrogens are way more reactive than the primaries, there's so many more of them. Okay, so just randomly, again, those radicals are so reactive, they're just going to find a hydrogen. And although we form the less stable intermediate with that primary radical, okay, we're still going to find more primary hydrogens. So we're just going to go and react quickly. Okay, so even though tertiary radical is more stable of an intermediate, it's more stable, the product from the primary radical is the major product, is major, right? It's greater than 50% compared to the other product. And that is simply because there's more primary hydrogens. Okay? So it's both the reactivity and their difference, but as well as the number of hydrogens that are present. Okay? It's both the stability of that intermediate as well as the number of hydrogens that are present.